To understand such transformations between input and weights and bias, we need to recall several definitions. And one of the most important definition is a matrix multiplication rules. In our example, we have 3 features and 100 samples. So W, capital W, it's a weights matrix, and B is the bias term. For the weights, we have only 3 features: W1, W2, and W3. B is just a scalar, and let's say it equals 1. It's a bias term. And our input matrix X, it equals something like, for the weights matrix, let me transpose this vector to the form like this: W1, W2, and W3. And we will multiply the input matrix X times the weights matrix W. W in this case is a vector, but let me follow the matrix multiplication notation. So then plus B, and it equals Z. The first operation, it's a matrix multiplication right over here, X times W. When you need to multiply matrix times matrix or matrix times vector, we need to remember about the matrix multiplication rules. To build an intuition behind the matrix multiplication, we need to recall the definition of the dot product between vectors. It can be expressed like this: vector A times the vector B equals to A1, A2. And for the second vector, we use the column notation, yeah? B1, B2. We need to multiply each corresponding items from the vectors and then sum these products. It looks like this: A1 times the B1 plus A2 times the B2. And let's come back to the matrix multiplication. Let's say we have matrix A and matrix B. First and commonly used method to express the dot product between the matrices A and B is to multiply rows of the matrix A times the columns of the matrix B, and we will multiply it accordingly with the definition of the dot product between vectors. So it's gonna be equal 1 times 2, because we need to multiply the corresponding items of these vectors, and we have 1 right over here and 2 right over there, and we need to multiply 1 times 2 plus 2 times 3 as the first item of the matrix. So for the second term, we need to take the second column from the matrix B, and it's gonna be equal 1 times 1 plus 2 times 0. Then we need to take the second row from the matrix A, and we will do the same, yeah? So 3 times 2 plus 1 times 3. For the last item, we need to multiply 3. It's right over here, yeah? Times 1 right over there, and plus 1 times the 0, yeah? Times 1 plus 1 times 0. And finally, we have something like 2 plus 6 equals 8. 1 plus 0 equals 1, 6 plus 3 equals 9, and for the last item we have just only 3. So it's a good way to understand what's really going on behind the stage when you multiply or express the dot product between matrix and matrix. Let's analyze the dimensions of the matrices. And we have 2 rows for the matrix A and 2 columns. We have the same number of rows and columns for the matrix B and for the output matrix. We have one requirement for the matrix multiplication. The number of columns of matrix A should match with the number of rows of matrix B. We use a row from the matrix A and a column from the matrix B. We have one requirement for the matrix multiplication. The dimensions of the column space of the matrix A should match with the dimensions of the rows of the matrix B. Because when we multiply matrix times matrix, we take the row from the matrix A and we have as much items as the number of columns, basically. And for the column size of the matrix B, we have as much items as the rows of the matrix B. So it means that these dimensions in the middle should match. If we will follow this logic, we can take only one column from the matrix B and it will work. It will work as a matrix times the column. Let's multiply A times the column of the matrix B, B1. Okay, and we need to multiply 1 times 2 plus 2 times 3, and for the second row we multiply 3 times 2 plus 3 times 2 plus 1 times 3. Okay, and it equals 2 plus 6 equals 8, and 6 plus 3 equals 9. It's very interesting because this result matches with the first column of the matrix dot product between A and B. It's absolutely the same result. Now let's analyze the dimensionality of the matrices. We have matrix A 2 times 2 times the vector B, and we have 2 rows and only 1 column. And for the final result, we have a vector, 2 rows and 1 column. And now let's think for a little, What if we take just only first row from the matrix A and multiply it by the matrix B, In this case, we have 2 columns, and only 1 row. And I think that it should work. Let's try to do this. We'll take the first row from the matrix A, multiplied by the matrix B. Okay, and we need to multiply 1 times 2 plus 2 times 3. And as the second item, we have 1 times 1 plus 2 times 0. And it equals 2 plus 6 equals 8, and 1 plus 0 equals 1. By this way, we just reproduced the same row, as for our matrix multiplication, as for the dot product between A and B. Now let's analyze the dimensionality. We have 1 row times 2 columns, and we have 2 rows times 2 columns, and it equals one row and two columns. In the first example, we reproduced the column from the output matrix of the dot product between A and B. For the second result, we reproduced a row, yeah? So in general, if we take a matrix A with m rows times n columns, multiplied by the matrix B with n rows times p columns, it will be equal matrix C with m rows and p columns. And you can see that it works, yeah, in our examples. Yeah, it's strictly just the row dimensions of the first matrix and the column dimension of the second matrix in the final output. So in deep learning, we always follow this quite simple rule, yeah? You need to keep in mind that the dimensionality of the column space of the left-hand side matrix should match with the row space of the right-hand side matrix. In deep learning, we always use this quite simple rule, yeah? And most of the time, you don't need to think about the numerical computations, yeah? You just need to think about the dimensionality of the matrices or dimensionality of the layers, yeah? Or whatever, yeah? Because you always have this kind of operations under the hood. But this is not the only way to do the matrix multiplication. Yeah? I can show you several more ways to do the matrix multiplication. We can take a matrix A and multiply it, first of all, to the first column of the matrix B, and then do the same for the second column, yeah? Because as far as I remember, when we multiply the matrix A times the first column of the matrix B, we completely reproduce the first column from the output, yeah? If we will follow the same logic and take matrix A and multiply it by the first column of the matrix B, and then do the same for the second column, reproduce the output of the dot product between A and B, yeah? So let me show you how it works. We just take the matrix A and multiply it by the first column of the matrix B. And then we do the same, but for the second column of the matrix B. And we need to multiply 1 times 2 plus 2 times 3. And for the second row, 3 times 2 plus 1 times 3. Okay, and now let's do the same for the second operation. 1 times 1 plus 2 times 0. 3 times 1 plus 1 times 0. And it equals 2 plus 6, 8. For the second column of the first row, 1 plus 0, 1, 6 plus 3, 9, and last but not least, 3 plus 0 equals 3. So in this result, it's absolutely the same, yeah, as in our first way to do the matrix multiplication, yeah? We can do the same for the rows, yeah? What if we take the first row from the matrix A and multiply it by the matrix B, but in this case we need to stack these operations in the vertical mode. I mean, we need to take the first row from the matrix A and multiply it by the matrix B. And for the output, we have 1 times 2 plus 2 times 3. For the second column, we have 1 times 1 plus 2 times 0. Okay, and then we need to multiply 3 times 2 plus 1 times 3 and 3 times 1 plus 1 times 0. So, and you can see that we have the same matrix, yeah, and result, of course, will be the same. Okay, and when we multiply the vector for this example, yeah, times matrix, yeah, we just shrink the dimensionality of the output, yeah, because we just follow this simple rules, yeah, of the matrix multiplication. But it's not always the case. I can show you one interesting example. For this example, we have 3 rows and 1 column for the first item, and we have 1 row and 2 columns for the second item. The dimensionality of the column space of the matrix A equals the dimensionality of the row space of the matrix B. So it's absolutely legit operation. We can run it, yeah. And as the final result, it should be 3 times 2. And for the output, if we follow this dimensionality rules of the matrix multiplication, we have 3 times 2 dimensions for the output. As far as I remember, the dimensionality of the column space of the matrix A should match with the dimensionality of the row space of matrix B, and it will work by somehow. Let's try to compute the output. So we need to take first item and multiply it by this and by this items from the matrix B. So it's gonna be equal 1 times 1. For the second item, 1 times 2. Yeah, and for the second row, 2 times 1, 2 times 2, and for the last row, 3 times 1 and 3 times 2. And it's going to be equal 1, 2, 2, 4, 3, 6 as the final output. And we can apply the same logic for the matrix multiplication. It's my favorite way to do the matrix multiplication. So for this last method, we can take a column from matrix A and multiply it by the row of the matrix B, like this. 1, 3 times 2, 1, plus the second column of the matrix A times the second row of the matrix B. And it equals to 1 times 2. For the second item, 1 times 1. For the second row, 3 times 2 and 3 times 1, plus 2 times 3, 2 times 0, 1 times 3, and 1 times 0. And it equals to 2, 1, 6, 3, and plus 6, 0, 3, 0. And finally, we have 8, 1, 9, and 3. Yeah, because we just sum every corresponding items. And it's fantastic. We just have the same output as before. Yeah, it works. Yeah, this way works fine. Now let's come back to our example, yeah? And we know that our matrix X is 3 by 3 dimensions, yeah? And we know that the matrix W, it's 3 rows and only 1 column. And then we need to add a bias term B. Yeah, but it is just a one number. Yeah, we have just a scalar. Yeah, it equals 1. And we know that X times W dimensionality, it's 3 times 1. And then we need to add this scalar term. And this operation, it calls broadcasting. Yeah, it's not about the linear algebra, but most of the frameworks or libraries like PyTorch or NumPy follow the same broadcasting rules. The broadcasting operator is a way to apply an operation on arrays of different shapes. The broadcasting is a way to apply operations to arrays of different shapes. It compares each dimension from right to left side. And in our example, we have one column dimension for the matrix A and 4 column dimensions for the matrix B. And dimensions of the matrices should match or must be equal 1. In case if we have just only one, we just stretch the dimension, yeah, and align it with the dimension of the matrix B. In our example, we stretch this dimension to 4 because we have 4 column dimension for the matrix A, and we stretch this dimension to 3. And we sum these matrices, and the final dimension will be 3 times 4. For example, we have matrix A, it's just a vector, yeah, but let's just call it matrix, yeah. 1, 2, 3, and the row vector, matrix 1, 2, 3, 4. We compare the dimensions from right to left. For the matrix A, the column dimension equals 1, and we need to stretch it to 4, yeah, accordingly with the number of dimension of the matrix B. As far as I remember, it equals 4. And it looks like this. We just copy our column, 4 times. And for the matrix B, we stretch the row dimension to the number of dimensions of the matrix A. And absolutely by the same way, we just copy the rows of the matrix B 3 times. So, and now it looks good, yeah, we have the same shape for both of the matrices, and we can run the sum operation. And finally, we have the result, yeah, it works fine. We can program our example of the broadcasting, and you can see the matrix A, and it's just 3 times 1 dimensions for the matrix A, and we can and now it looks a little bit more obvious that we have 3 rows and only 1 column. And the matrix B with only 1 row and 4 column, yeah, and shape equals 1 times 4. Let's perform the broadcasting addition. A plus B. And there is no surprise, yeah. It's the same result as we did with pen and paper, yeah. So we can check the shape of the result A plus B, and it's 3 times 4, yeah. Works absolutely as we expected. By the same way, we can do the matrix multiplication. And you can see the result, yeah. We run the matrix multiplication, yeah, with this at symbol. It's just the dot product between matrices A and B. And you can see that the shape of this operation, it's 3 times 4, exactly the same as for the addition. And the matrix multiplication result, it's right over here. It works exactly as we expected, yeah? No surprises. And now let's come back to our example, yeah? We have this b is just a scalar, yeah, with dimension 1 times 1. And for the first operation, we finally just squash these dimensions, yeah, and have 100 times 1 dimensions, yeah, plus 1 times 1. We will apply the broadcasting rules, yeah, and we do this from right to left. This dimension and this match, it works fine. For this pair, we have 1 and 100, and we just stretch the dimension of the b to 100 times 1. And finally, we have an output with 100 rows and 1 column. So it looks nice, and the most important information condensed in the matrix shape. You always need to follow the dimensions of your matrices.